expression.
Look at you.
Wow.
Damn, pretty good.
Guys,
Pretty good.
I've been waiting.
I won't start
I've
running
been
shit yet.
waiting.
My whole life.
She just
It's
went
good.
into that question.
What do you think chaos is?
You.
Oh shit! I can't believe you went there before 10.
I mean,
It's
it's
a little
close.
early.
It's almost 10.
It's like
Yeah, it's, yeah.
not ordered. Like things are just
It's like the absence of order.
what she said
Yeah, but which is exactly what you said.
in better wording. Yes.
Absence of order. Anything else? Cool. Anything else from the south?
Does it make sense that something that is ordered is also chaotic, though?
Yeah.
This is not a mathematical example, but this is one that I've been experiencing recently. When you go into the grocery store and, like, on the rare occasion that the whole aisle is full and, like, you don't see what you're looking for, it's all just blurry because it's full. That's what I'm trying to say.
That
Very
yeah.
ordered, but it's not,
It's an overwhelming amount of order.
it's chaos.
Yeah. So like there's some structure, right? There's potentially structure.
Yeah, there's structure, but it's so structured that it's, like, no longer useful.
Yeah. So like chaos and structure aren't necessarily mutually exclusive ideas.
Yes.
Yeah.
Yeah.
What's life?
Chaos.
Some combination.
It's
therein.
yeah. So like, is there anything linear in this world? Like really, like actually linear? Weird. Or is it all just bullshit?
Yes. Yes.
Yeah, I'm of that mind as well.
Yeah.
Linearity's just, it's a good idea. It's kind of crazy it works. I think it's amazing that anything we do with math and science actually works because it's all just kind of lies. Like really subtle lies. Right?
This works most of the
Your
time.
entire life, it's a lie. But like, here's an equation.
Let me show you let's watch some movies to warm up.
Yes.
So I wanted to show you some examples of chaos, and I've got them up in our course page, which was really barren, so I felt like it was just like, this looks desolate. So this first one, let me grab a pen because I do need to like draw shit. This is called the Lorenz water wheel, and you can see this is a pretty down-home version of it. But the basic idea is you've got a water wheel and you've got these little buckets. Yeah, wow. These are bad buckets. You've got these little buckets. I'll just stop trying to make them rhombi or something. Trapezoids. Okay, so then you have a water source that's leaking water into these, and then there's a little hole in each one at the bottom, so they drip out all the way. And so you can see that here. This person rigged a bike wheel at a slight angle with nice styrofoam cups. Well, styrofoam cups aren't nice, but styrofoam cups around, and I think they're just using a faucet. And I just want you to watch the behavior of this. And I hope we can get some sound because there's actually like a lovely. Well, let's go to the actual YouTube version so we can get some sound. So just watch the motion of this. Looking pretty reasonable, right? You know, it's just like it's rolling. Seems like that should continue onward. This is about as far as my wife would make it through this morning. I tried to make her watch this. She said, okay.
She said, sure. Absolutely. Well, that's just wrong.
And then, then all of a sudden, things change. I'm narrating the obvious. Sometimes it really gets cooking too. This is only a 3-minute video, so don't fear. So I wanted to get funding for Regis to build a really nice one of these, like on the campus.
It could be like a fountain.
It would be a beautiful
It
fountain.
would be so pretty.
So this is an example of chaos. So that the speed at which that water is flowing is a parameter in this system. And it's really the only parameter we have control over. But for certain volumes of water coming through there, per minute, whatever, this acts normally. But if you get just the right volume of water, the behavior becomes completely unpredictable. So notice there is structure, right? There is some structure here. But there's also this element of unpredictability as well. A slight change in the volume of water per minute can change this behavior in a heartbeat. Another example. So that thing.
Lightsabers are finally a reality.
Whoa!
Yeah. Sorry.
Everybody chill out.
This one's sick.
Ow.
I say it says slick double pendulum, but it should say sick double pendulum because this is freaking. This guy did a lot of work.
Cool.
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 Hey guys, Devin here with Make Anything. Now, a lot of you in previous videos have seen this giant disc on the wall, and you're asking me what that thing is. Makes sense, it's pretty funky looking, and I figured it's time I explain. After all, it is one of my very favorite projects that I have ever done. A few of you recognize that this is, in fact, a double pendulum, which is a really cool mechanism that demonstrates chaotic motion. That means even a slight difference in how you swing it will lead to wildly different results. I made these arms by laser cutting smoked acrylic, and then I fit some skateboard bearings in them to make them rotate. And then I also have this 3D printed structure holding it in place. Now, double pendulums are super fascinating as they are. They do some really crazy movements like that. And you see that? That's just weird. It does a lot of weird stuff. And I wanted a better way to visualize it. And that's where this becomes extra cool. This is a little battery pack that I 3D printed to hold two 3-volt button cell batteries. It's also got little slots to hold onto an LED. Now, this isn't your ordinary white LED. In fact, this one emits light at a wavelength of 405 nanometers, putting it on the UV spectrum. Now, this entire disc is coated in a photoluminescent pigment, otherwise known as glow-in-the-dark paint. Combine that with the UV light, and you've got something kind of awesome.
Whoa. Yeah. Yes. It's really cool.
How cool is that?
Very.
And it only gets crazier when you turn off the lights. So, UV light, glow-in-the-dark paint, and a double pendulum. Do you see what I'm getting at here? Oh yeah. Let's do it.
Yeah.
The bottom of the pendulum here is made just the right size to hold on to this battery and the LED. There we go. We now have a very cool way of visualizing the path that this double pendulum takes. So why don't I give this a quick spin and then we'll turn out the lights.
Don't you want one?
Oh.
We should make one of those.
We could actually
I
do that.
vote we do that.
That's crazy.
Oh wow.
So can you see why this is one of my favorite projects? It is especially cool, especially in person, not to make you jealous. Now, if you're like me, you could probably watch this for hours. And that's why I made a second video of just the pendulum spinning non-stop for a very long time.
Can we watch that?
So you guys should check that out. In fact,
I'll
while we're
I'll
looking,
joke with it.
I want you guys find a really cool moment in the pendulum swinging and link to it in the comments of that video. Whichever one gets the most likes, I will send this awesome little glow-in-the-dark coral reef that I made in my Scribbler 3D pen video.
I want that.
I think it could be fun, especially since there are some really weird movements that this double pendulum does, as you guys will see. If you guys would like to own one of these one day, make sure to check out the link in the description where I have a little product page set up for this pendulous, and you can sign up with your email and get notifications if anything ever happens with it. I think it could be a good Kickstarter campaign. Alright guys, there you have it. One of my very...
Flood project, actually.
What if we made it like a, not like similar to the fountain idea, where it like lived somewhere on campus?
Yeah. Oh yeah.
I could dig that.
That would
Like
be
have it hooked up to the wind maybe somehow so that it like could.
kind of like a turbine.
Yeah.
We could generate electricity.
Wow.
This is growing. That would be the least effective electricity generator.
But it's the thought that
seeing
counts.
as it's chaotic. But it works 20% of the time.
I like where your head's at.
Thank
I
you.
really do.
I'm just trying to get you funding, okay?
I appreciate that.
I want them to never let this class end.
That sounds really good. We
Well,
have so much I want to do. It's like there's no fucking way we're gonna do it all, but
Virgo.
this is the last one. So this is trying to get a little bit of different physics and chem stuff. This one's very nice. Oh.
Yay.
Check this out. I'm going to show you how I afforded this car.
No, no, I should have.
Okay, you ready?
I made the big mistake.
100.
Go, go, go.
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 Oh my gosh.
Any heard of this?
I think we talked about this one day.
So like this is beyond my ken, really. I don't.
Like,
Oh,
that's
no.
this.
Boy, am I excited. A little twirly, absolutely. Interesting.
So you've seen some stuff happening kind of already that's like indicative of the reaction. It's like oscillating chemical reaction.
At my internship this summer, I had a chemical, like my product actually did this.
Oh, really?
Randomly, yeah.
Wow. So I'm curious, did it like do something like
It's like, oh,
What is that?
oh, but that's super cool.
Oh, I love that.
it's beautiful.
Waves of blue just pulsing across it.
It's like a million times cooler than a lava lamp.
Yeah, absolutely.
We can
Yeah.
make one of
Yeah, I think yeah,
those.
absolutely.
We have all of those items. I could go grab them off the shelf right now.
Right now. Honestly.
Yes.
They're pretty common.
Bring us some safety
I think
glasses.
so. We can't do that in here.
I
We can meet up in a lab. That would be cool.
mean, secret meetup.
I mean, I have access to all the labs.
I like the music we put behind it.
It's interesting that at the edges it's just turning blue.
Yeah.
pretty good.
We're still going.
Seems like it's reached equal.
It's turning white though.
Oh, yeah. I mean, the music's indicating this isn't over.
This is not.
Oh, there's little waves.
I'm right in.
Yeah. Okay. No, do not speak a word.
Okay.
So, all examples of chaotic systems and all things we can study in this class. So one of the things I kind of wanted to do is, we're not gonna have any exams,
Good.
cause I fucking hate exams. Like, and every time I'm about to have one, like if you've had classes with me, you know I try to like I'll say, we're gonna have 4 exams, and then like, it's like, can we just have 2? And then, like in abstract, right?
That
was
was
like,
so fun.
it was just like,
Our first exam, he said, yeah, I'm gonna need you to memorize these definitions,
And that's it.
and that's it.
And
Oh.
rated it very generously.
Very generously.
I remember you walked in one day during Reel and you were like, I'm not feeling it. We're not having an exam. Do you remember that?
oh,
I expect nothing less, truly.
You're like, we're not doing
it sounds like something I'd said.
Well, yes.
I do like the definition exam. That sounds like a sick exam.
I mean, it was sick, and most everybody did okay on it, sadly. So,
I didn't get 100%, I'll tell you that much.
nobody did. Wait, maybe one person
Did
did.
you get 100%?
Yeah, one
Wait
person.
a second, that's a
I
lie.
know, I'm like, one person, there was one
Wait a
person who got 100%.
I worked my ass off memorizing those definitions.
You
What
did
do
good,
mean?
you
I'm
did
so proud of
good.
you.
And then from there, it was,
Definitions in abstract or like?
Rough.
It wasn't that bad. It was at the beginning of this.
Excuse you.
yeah.
Oh, okay.
They
So
were
it
rough.
wasn't like one of the ones at the end. that's,
Yeah,
like,
it wasn't
half
like
a
a
page
garbage.
long.
Yeah.
Did we even have another one?
No.
It was a take home.
The final.
It's
Final.
just the final.
It was like homework.
Yeah.
It's just a slightly harder homework.
Yeah.
Yeah.
That you still could get help on.
Unlike our numerical one.
That one was.
Was that brutal?
It was just long. It was really long.
I think it took me combined more than 24 hours.
It took
Simply
me.
because
It took me a while because he said we hadn't done like specifically like physics problems before, like in class, and then suddenly more than half the
7
exam is
out of the
physics
9 problems on the exam.
Oh
I
shit.
was like, so this is fine for me, but like, what about all these other people in here?
The non-physics person, I was like, hey guys,
Help.
Well, the cool part about being a mathematician is you can do like lots of stuff, right? Like with math, so
Yeah.
you can't understand it necessarily. Like I don't know what
Right.
mass is, but I can do shit with it.
I don't know it
I can
actually,
just
but
do
like
it.
here it is.
It's okay. Physicists are basically like that anyway. We don't know what the fuck's going on. We know how to do it. So it's fine.
What am I doing?
And act like you know what the stuff
Oh
is.
yeah, absolutely.
Throw some units on the end of it, call it good.
So like instead of exams, what we're gonna do is I'm gonna have you all like present some problems occasionally.
That's worse.
Did you say that's worse?
You're welcome.
It's only us in here, Trinity, it'll be okay.
Yeah.
It doesn't matter.
We'll
Yeah.
face the back.
If you want, I'll turn around.
I used to have to teach every week in one of my physics classes, and it was the worst experience of my life. It'll be fine.
But we think
It
you're
will.
cool.
It will. It's not gonna be like anything you can't handle. You can. Oh come on. You
She's
can
like,
handle it.
Is it like go and find an example of chaos?
No,
Here
no,
is an
I'll give
example
you,
of- okay, cool.
like, I'll like say, hey, could you just do this problem and show us how to do it? Occasionally.
Okay,
And it's not even gonna be that much. And like, that's what I say now, who knows what's gonna happen. So like.
We're
so-
gonna get to the end of the semester and be like, hey, I never presented a problem.
Well, what I kind of wanted to do, so like my original idea was at the end of the semester, instead of a final, like each of you just pick an example of something that involves chaos and just show that to us, something you love and you're passionate about, like in your discipline, you know? So
So I thought that sounded kind of fun and casual. And our final is scheduled for 8 a.m. on a Monday, and we are not fucking doing that.
No. That's what our final for Abshock was supposed to be.
And I think I said
He
the
said
same
no.
I don't do
Absolutely
8 a.m.
fucking not.
finals, no, unless it's for calc where I have to do
I
something.
would do 8 a.m. in general.
Required to be there.
I'm required to be there, yeah, so like a lower level class. So that'd be like, I was thinking like 25% of the grade would just be just simply doing that, and then the rest is homework. Everything else is just homework.
Cool.
Does this sound okay?
Yep.
Yeah? And your first homework assignment I have for you.
Of course you do, Dr.
Of course
D.
I do.
What does it do?
So, yeah, hold on.
Hold on.
So 221, 223, this is, and I am going to push you all a little harder than I would other people because I have great respect for your abilities. Sorry.
Sorry. I don't think I've ever heard someone apologize for that.
And some of these are not, this looks fairly long, but it's actually not. There's not a lot to do. Don't get crazy, you don't have to get crazy with your homework. You know, I know you all write up nice homework, so don't spend a lot of time trying to make things super beautiful or anything like that. And I guess what I kind of like is if maybe you could also read chapter 1, which is stuff, it's just really a narrative. It's not even technical, it's just like the history of the study of chaos. And it's good. This book is awesome. Strogatz is a really great expositor. He's a very entertaining guy for a mathematician kind of guy. He's also kind of square, but he's also kind of cool. And so he's a really great writer, and I love the flow of this book. I used this book in grad school. So this is like a graduate level book, but it's written in such a fluid way that it's pretty accessible. And there's nothing in here there's some stuff in there I don't understand, just to be straight up with you. It's pretty heavy at points, but it doesn't start off heavy. In fact, the first thing we're gonna start talking about is lovely, one-dimensional flows. We're not gonna get to chaos for a little while. We kind of have to build ourselves up to, yes.
Projected due date.
Oh, projected due, that was the first question that I passed off.
Oh, word.
How about next Wednesday?
Sure.
I mean, when we meet 2 days a week, there's part of that I love and a part of that sucks because we don't get to meet on Fridays. Oh yeah, and my office hours, like for you all, like just whenever I can meet you via Zoom, but I better put that up here. I have a syllabus, it's posted.
I read through your
It's
syllabus.
pretty shoddy.
I like the section on cell phones.
Oh, did you read it already?
Oh
Yuck.
yeah, of course I did.
Oh wow,
It's
nice.
the end that says yuck for me.
Yes.
It made me really happy. I laughed out loud.
Wow,
I really did.
oh,
I was
nice.
like,
Yeah. Oh, so you can just look there for my office hours, but I'll put them up here. So let's see, it's after my calc class, so I think it's like 12:30 to 2 Monday, Wednesday, and then Tuesday I'm not available for anyone but you all in the afternoon. I can meet you all in the afternoon via Zoom. On Thursday, I've just got all these other commitments on Tuesdays and Thursdays. I like lead this international yoga meditation group, and then
I expect nothing less.
yeah, and I've got like I've got to meet with my own Zen teacher on Thursday and stuff. So, but Thursday, I think I said 2 to 3:30, and that's a Zoomie. But again, literally it says on the syllabus, any time for you all. So like, you just let me know and we'll figure it out. And then Friday, I like by appointment, because I might want to just leave after calculus.
Are you
So-
on campus on Friday though?
Yeah, I am. So this could be in person. On Friday, we can meet in person. And I could meet with you all. I could meet early too. So like I teach from 11 to 12. So pre-11, not too pre-11, not too pre-11, not too pre-11 on
so
Friday.
7:30 is not the vibe.
Correct.
Okay, just
Correct, Matt.
Off the
Yeah.
table.
Just think of like 10.
Okay, yeah.
If it's earlier, I would meet you by Zoom. Gladly.
Perfect.
Absolutely. Like, and Zoom all the time. I like fucking just like Zoom like crazy. So I just don't like leaving home.
Same.
Yeah, right? So you get
Me
it.
too.
You know, it's like I'm just like I just want to be at home, but I love you all so. Cool. So what we're going to study are flows on the line for a while, and then eventually we're going to study flows in the plane, and we'll do one of my favorite examples that Strogatz created, which is a modeling of a love affair between two individuals, and it's created with math, and it's just fucking amazing. But first we'll start with flows on the line. So this is just one person loving them. I just like we're okay, I'm just gonna stop with that. Loving themselves, which is good. We should all love ourselves. So got a line, and the position on this line is x, and we'll set an origin. So x equals position on the line, and we'll we'll take a small unit where we study flows on a circle, which is a whole different dynamic going on there. But for us, it's just an infinite line. And the motion is going to be governed by the following map. So we have x dot, which is dx dt. T will always be our independent variable for the whole class, because we're really interested in applications. Strogatz has a great quote that he said, since Newton, we've come to realize that the laws of nature are governed by differential equations, or at least modeled by them, right? So all scientists think in terms of differential equations. This is the language of science. This is how we understand change in the world and work with it. So we have this rate of change, dx dt, and let's come back up here, is governed by an equation. So let's look at something we'll rarely actually look at. Notice that the rate of change here depends not only on the position, but the time as well. Position and time. So this is called autonomous. Wait, is that nice? Now I can't remember which one's non-autonomous, and I'm trying to think. Yeah, this is non-autonomous. Okay, yeah, that makes sense, because it's not like self-contained. So this is non-autonomous. And we're not going to really do much of that at all. There might be a few examples from here and there that come up. But for us, the primary focus is going to be, so our focus is autonomous systems. So we're going to have x dot equals f of x. Rate of change depends solely on the position. And so you can think of this x dot as a little vector here, right? So if I'm at position x, x dot is my velocity. So there's x dot positive. If I had an arrow moving this way, that would be x dot is negative. And then if x dot equals 0, what do I have? What happens if x dot is 0? So x dot positive is motion that way, x dot negative is motion that way. What's x dot is 0? Say what?
Just x dot. It's
No motion. So thinking in terms of motion. So like that's stop, that's stationary. That's a stationary thing. So x dot equals 0 means no motion. And we call that stationary. Which makes sense, because that's what stationary means. You're not moving. So let me give you one here right off the bat. Here's x dot equals kx, and k is just a constant. Now I want you to notice something. I'm not giving initial conditions. So most of the time in physics and things like that, when you're actually modeling something, you have an initial condition. So you would have something like x at time 0 is an initial position. So this would be an initial condition. We're rarely going to worry about initial conditions.
What we're interested in is understanding how the flow on the line behaves qualitatively. So we're interested in, if I start here, what do I do? If I start here, what do I do? Are there any other places on the line where the behavior changes qualitatively? So I have to go pee really bad, really bad. So what I want to do first though is ask you if, and you can discuss this, please always discuss stuff. Could you solve that differential equation for me, please? Be right back.
After I go pee. 'Cause I also have to pee. I love that man.
I'm so stoked that we got to have this class. So I'm not the only person who spent 9 million years on the numerical final.
I spent more than I wanted to.
I was less than impressed, we'll say.
Thought it was unnecessarily difficult.
What all are you taking this semester?
I'm taking electronics, which I don't want to take because it has a lab, unfortunately.
What
And
does
then
that lab look like?
building circuits and things, probably.
Hi. We got anything?
She had a pizza.
Okay. Yeah.
She didn't
Woo.
just leave.
The world is so much better now. Maybe a little light. Is that okay? Just a touch. I hate the lights in here, but ew.
If that makes it better or worse.
I bet you'll be able to see better. Let's look.
Oh yeah, yeah.
Yeah,
All right.
super good.
Thank you. Do we got? So we got anything? Anybody got anything on this?
Yeah.
You do?
Oh, well, now I'm concerned.
No, it's okay. No, I mean, it's not. You know.
Okay.
What you get? How'd you do it?
I isolated my parts. So I said, I got the x's with the x's.
Nice.
So dx over x
Yeah.
equals k dt.
Beauty. So you separated the variables.
Yeah, I said that really weirdly, but yeah.
No, it was great. No, it's good.
That is
It's-
a tactic utilized.
Yeah, yeah, absolutely, perfect. And then what'd you do?
I integrated both sides
Cool.
to get ln x equals kt.
And I'll just do that, but it's, you know, it's cool. In the end, you mostly forget that. And is that, did you stop there? That's great, that's cool. This is a solution. This is great. No problem. How do I get x?
It would be e to the kt times e to the c.
Lovely. So take the exponential of each side, and then we get, and we'll strip off x. Well, here, actually, I'll leave this here for a minute, just to talk about the subtlety. So we get this, right, like that. And then, feels a lot better, doesn't it?
Life is better. And this is what you were saying, I think, Kayla? Yeah, so at this point, this is totally valid because we've got absolute value and both these are positive. But if I would like to allow x to take on other values, I could strip off the absolute values and make this a constant c, and we get this. Nice, 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 nice. So, now when we did this for any k, except k equals 0, if k equals 0, what would the solution be here? Actually, let's just do that really quick, because we're doing all, what's that? I'm sorry.
X would x equals 0.
Or constant, right?
Right,
So-
after integration, yeah.
Yeah, after it. Oh, I see, you were separate. Yeah, you can't, yeah, separate, yeah, I see. You went like this. Yeah, like that. And then x is just equal to some constant. Right? So we just have x is a stationary point at that. So let's take a look at this. Now we're gonna come back to this because we're gonna have simpler ways to look at this. This is like when you take diffeq, you spend a lot of time learning how to do this stuff. And then you could plot the solution. So if k is positive, first off, if k is 0, the solution is constant, so I'd have something like this. Right? K equals 0, just a stationary solution. What does it look like if k is positive? And let's say c is positive as well, maybe. What does this look like? So sometimes it helps to have a real thing. So like x equals e to the 2t. What's that do? Give me a finger. Yeah, there you go. Exponential growth, right? So, and exponential decay as we move out this way, right? So as we move to the left, we have decay. As we move to the right, we have growth. So this would be k is positive. Like that. Does that sound okay? And then depending on what this c is, this is going to cross the axis at different points. In fact, the place where it crosses the axis is exactly c, because when t is 0, x is just c. Look at that. What about when k is negative? So like let's say here k is negative, so I have x equals e to the negative 2t. What do we get then? yeah. Like that, right? So there's k is a negative number. So I want to point out something here. And this is all for c is positive. If c was negative, like I had a negative number in front of this was x equals e to the negative, x equals negative e to the 2t, so like this. I would have just the flip of that. So this would be k is positive, but c is negative down here. And then you still have this moving away. The key thing for this is I want to point out what we get is this motion away from x equals 0. And when k is negative, so for example, if this was x equals negative e to the negative 2t, it's just this graph flipped over, so you got like this. And here I have motion toward the x-axis as time progresses. So this is all really complicated and it takes a lot of work, and sometimes this could take a lot of work. And sometimes it's actually not even possible to solve the differential equation. So what we're going to do is talk about some ways to understand the qualitative behavior, understand what I just said here about growing away from, growing towards, in other words, instability versus stability, by just analyzing the original equation. So that's kind of one of our main goals in this class, and it's going to be a key tool for us. So let's take a look at a different way to look at this. without solving it. And in a couple of your homework problems, you get to solve them, but they're not super painful. And we'll do one together that's kind of like that, like we always would. So let's take, ooh, that's a much better pen, a different approach. I feel like I spend a lot of time oohing and ahhing about pens in my classes, don't I? Yeah. This is a qualitative approach. So we're going to look at something called the phase plane. And what we're going to do is we're going to take the system x dot equals f of x with no initial conditions. And we're going to plot it kind of like it's like y equals f of x. So this is going to be x, and this is going to be the rate of change. And we're going to plot these things out. So let's look at this first one here. Let's say, so we had x dot equals kx. And let's just take k as positive to begin with. What shape would that be here? A line, yeah, linear. Yes. Yeah, so y equals 2x, y equals 3x, whatever. It looks like this. So where that curve crosses the x-axis, we have the rate of change is 0. We get a stationary point. So stationary point whenever that curve crosses the x-axis. And I should, yeah, I might do something here in a minute. I might not leave that solid, so maybe just draw a little circle, unless you already have, and it's all good. So notice that to the right of this stationary point, the rate of change x dot is actually positive. So see, the rate of change is positive. And that means that down here on this x-axis, which is our flow line, right here, x is always growing on this side. Does that make sense? Let me know. Tell me if that makes sense. What is x doing on the left? Decreasing, because over here, x dot is negative. And we're thinking there's this hidden t in here. We're not drawing the t. The t is hidden inside the little particle that we're imagining moving along here. So over here, x dot is negative, so you'd always move to the left.
Is that like radial motion? Because generally speaking, we think that x moves this way. Does that make sense? Even though x dot's negative?
I'm confused. Can you say a little more? Yeah.
It's like doing this,
Yes.
right?
Yeah,
So
yeah.
There's like circles.
So it's going out, basically.
It's
from
going
the station.
outward. It's not.
Oh,
negative.
yeah. Okay. Yeah. Yes.
Okay.
Yeah. I see what you're saying. Yeah. Yeah. We only have like one dimension here,
Right. So
but
x,
yes.
So we understand x's behavior based off of x dot.
Yeah.
Cool.
Yes.
Perfect.
100%. So this point right here has a unique, a lovely property. Well, maybe lovely, maybe not. If I'm on this point, if I'm right at x equals 0, I don't move. My rate of change is 0, and I'm stuck there, so I'm stationary. If a wind blows and I move the tiniest hair to the right, I'm lost forever, because I just keep drifting away from home. If I drift a little bit to the left, just the tiniest epsilon, I drift forever away from home. So this is an unstable stationary point. And usually we kind of leave those as open circles. In this book anyway, closed circles indicate stable, stationary points. So this is with k equals a positive number. Now look what happens when we have k as a negative number. Then x dot equals kx looks like a line with negative slope. That's a pretty sad-ass
here's x dot equals some negative multiple of x. Here's my stationary point, because that's where I cross. What's x doing on this side, on the right side now? Decreasing, because x dot is negative here. X dot is positive here. Is this rocking? Yeah? So what do you think we call that? That was an unstable, what do you think? Stable point. So we have a stable stationary point. Cool. So these phase plane diagrams are way easier. You don't have to solve the Diffie cube. Notice that we get the same information, that when x was positive, as time moved on, I drifted away from the equilibrium solution, x equals 0, no matter what side I was on. So right now, this is that portrait that's over there, this vertical axis here, and this place where it's intersecting is kind of that picture over there, but with a lot, like the guts showing. Cool, let's try another one. And I'm gonna ask you to do this one. What if I have, and then I'll do the painful part. I'll do the pain for us. I'll take it on my shoulders. So what if I have x dot equals x times 2 minus x times x plus 3? Maybe we'll all do this together. It's just so I can give you some tips on how to proceed. So first thing I'm going to do is I'm going to get a phase plane out. Because solving, I'm actually not going to solve that because it would be freaking horrible. And I'll show you how horrible it would be in just a second. But where are my stationary points? 0, because that makes that 0, yeah. And I'm going to leave them as open until I know otherwise. Negative 3. And 2. We see how we're getting that? It's when the right side is 0. So first thing I do is mark off my stationary points. Now I've got this polynomial. I kind of want to graph y equals that. And we don't fancy. All we really give a shit about is it above or is it below? Because the only time it can be 0 is at these points. This is a continuous function, so I know it can't do this and just all of a sudden jump. So I just have to figure out what is the sign in between here. Can you maybe do a quick little version of that for me? How would you proceed, actually? Let me ask. How would you proceed in getting a very loose graph of this, just like understanding the field and behavior? So I will attempt the god-awful thing on this problem I made up.
might be. I cheesed out. It could, yeah, I'm just like gonna say they are some values. Like, because you would have to use partial fractions expansion.
Yeah.
Does that ring a bell?
Yeah.
To try to do this. And then this is just log properties. But I don't think that's even solvable for X. I don't know how to solve that for X. Like, that's just god awful. So getting an explicit solution of this thing, X equals some function of T, is just pretty much impossible without having a computer do it for us. Some, Wolfram Alpha or something like that, MATLAB. Just ungodly feat. Doesn't matter. We can totally understand the things we need to understand. And that is what's stable, what's unstable, and how does the long-term behavior act depending on initial conditions. Anybody got a graph of this thing yet? Can anybody tell me a strategy for getting a quick graph?
You can always do like reverse derivative test.
Ooh, that sounds good, but a lot of work. I'm thinking like junior high level,
Oh, okay.
grade school level.
Oh, you like plug and chug?
Plug and freaking chug in a way, but with the savvy of a person who understands that continuity is in play here. So let me show you what I mean. When X equals 1, am I above or below?
Okay.
So I pick points in between these regions. I got 4 regions here that I need to pick from. Let's just start out here maybe. 1, 2, 3, 4. So when X equals -4, we've got, so X equals -4. X dot is, and I don't even care about values, negative times a positive times a negative is positive. So the flow here is positive because X dot is greater than 0 there. So that is at least stable on the left. Isn't that nice? Like, so much better. There's no calculus involved here except understanding that that is a rate of change. And then what about in here when X is -1? We get X dot is negative times a positive times a positive, and so that's negative. So the flow here is in this direction. And I know that that can't change anywhere because it would have to become 0 to change. So all these points here are my discriminators of behavior. So look, can we finish up the rest? What's the, you already got it? Yeah. It's this one. Yeah. And then, does that make sense? Yeah. And look at how lovely and quick that was. So now I can just classify all my stationary points. So stationary point, I'll make a little chart. And then the stability. So we've got -3, and that is stable. So in this book, we would color that in as a solid. This is unstable at 0. This is a stable at 2. That's it. And I want to talk in just a second. I want to talk about a subtlety of what is going on here. So notice how, like, just over here, all this kind of stuff, e's are hidden in differential equations everywhere. Exponential motion is really hidden in there. Notice how even though we were stable here as we moved towards 0, we never got there. We never arrived. It was asymptotic. When it was unstable, we never actually were there to begin with. So this motion here, like if you said, what's the motion? I'm gonna put a little leaf right here. So I draw a little leaf, and I put it on the flow, and I watch what happens. It moves this way at some indeterminate rate, but it never actually gets there. It just gets closer and closer as time goes to infinity.
So just make a note in your head or whatever that we never arrive. We just get closer as t approaches infinity. What else do we got here? Oh, yeah, here's a fun one. Let's try this one. Last one. Last one. Unless there's any questions about this. Here's another beast to solve. This one's actually solvable with some integration skill. But what if I have x dot is the cosine of x? Can you please sketch a flow for me? And of course, your step one would be applied. Oh, yeah. There.
And then this one's gonna go right that way. So not gonna stable. They're gonna be that way. So it's like an odd even issue. It's like every odd will be unstable.
Yeah, absolutely. What are your points labeled? The actual coordinates are a little off
Yeah, I did.
though. But then you got the right idea.
Did I simplify? Perhaps.
It's got the flavor.
I love
It's
that.
got the flavor.
That's what I'm looking
The
for.
flavor is there. What is the actual coordinate of that?
Pi over 2.
Pi over 2, indeed. I knew you knew that. And then nice pi over 2. We got too many cashews in my throat to do a good. Nice. Oh. So, stable, unstable, alternating, forever and ever, right? And there's infinitely many. And so we could, like, if we wanted, and let me just give you a little bit of more notation. They, in this book, we use an X superstar, which is a fun way to say it, but this X superstar here is going to equal, this means stationary point, this little asterisk exponent there. So we've got two sets of them here. When we have pi over 2 plus, let's see, I guess, 2 pi k? Is that, or is it pi k? It is, that's a 2 pi, right? There's a pi. Yeah, there's a pi, yeah, okay, 2 pi k. K is an integer. This is going to be stable. And then when we have 3 pi over 2 plus 2 pi k, that is unstable. And we have like 2 minutes left, and I can't let go. Where's the velocity greatest? So we know that the velocity is changing, and you're actually slowing down as you arrive at any of these stationary points. what, if you had the leaf on here, when would the leaf be moving the fastest? No, because it'll never get there.
Nearest, or like as close as stationary.
So it's actually slowing down. So as we approach a stationary point, we diminish our velocity. Because velocity is actually going to zero, right? At that point, because this is velocity. So if I write it like that, does that help? It's right at these peaks and troughs. Right? Because that's your height. Does that make sense?
Yeah.
How would I figure out when the acceleration was greatest?
I think that's what I was thinking about personally.
How would I do that? Oh, I see what you're saying.
The behavior of the velocity.
Yeah.
Look at the pitch.
So yeah, something like, yes, I think something like that. So, I think, I'm not, that word is a very scientific word. I'm not sure I fully understand it, but, what if, so, like, I'm thinking of like airplanes, like pitch and yaw or something like that, right? I could differentiate with respect to T again. Chain rule. And then x dot is actually cosine of x. And then I could plot this out and figure out where it reaches a max and a min. Yeah. And I could actually also know where the acceleration is 0 as well. When sine equals 0, well, cosine equals 0, I'm at a stationary point, so that's when I have 0 acceleration. That makes sense, because I'm not freaking moving. But then also when sine equals 0, I have 0 acceleration, which, when would that be? Probably at these peaks. Let's see, so sine looks like this. So right, yeah, at these peaks, I guess that's when my acceleration is 0. Yeah, just having fun more than anything. This is a problem in the book that I'm not making you do, so I wanted to talk about it. What y'all got next?
Meaning and making music. My RCCM.
That's could be good.
Our first assignment was to put your favorite songs on a Google Doc so we can listen to them in class.
Cute.
Wow, that's awesome.
Yeah.
That sounds really
Like
fun.
sick assignment.
That's gonna be a fun first day.
That's gonna be a fun class.
Yeah. Who's teaching it?
Fritz, Eric Fritz.
Eric Fritz? Oh.